Hello, everybody. So this semester, we're spending a lot of time building up a good knowledge of quantum mechanics. So a good place to start is actually with why we need quantum mechanics. So one of the classic places to start is by talking about black body radiation, which was essentially one of a series of classical physics problems that whenever you tried to throw classical physics at the problem, it gave you nonsense answers. So this was, again, a really important age in the development of chemistry around 1900. So one of the important things to remember is at about this point, not everybody was even convinced of the existence of atoms. The atomic model really wasn't a thing yet. So this was one of the things that allowed us to really build up atomic theory. So one of the big questions at this point was black body radiation. So you're probably familiar with the idea of black body radiation, even if you haven't heard the phrase. So black body radiation is simply the idea that if I take an object and I heat it up, it's going to release a continuous spectrum of light from the object. So you're going to have a smooth spectrum of light, usually peaking at a given wavelength. So depending on the temperature, that wavelength will essentially shift and the color of the object will change as well. So you're maybe familiar with this if under the idea of, say, if I heat up a piece of steel or metal really hot, it starts to glow. This is black body radiation. Old incandescent light bulbs, which is really just a tungsten wire that you run so much electricity through it that it generates so much heat that it will start to glow. That's again black body radiation. And then, of course, the largest black body source in the solar system, the sun, which is essentially a giant, very hot object which releases photons through black body radiation. So we often end up truncating this idea or model as essentially a solid or a hollow sphere where we have essentially light bouncing around inside the object of interest and essentially slowly being released through essentially, in this case, a pinhole. And what we're really going to be doing is trying to line up the detection of the light emerging from this object with what's happening on the inside of the system. So we can start with a set of classical empirical observations, so things that can actually be measured about black bodies. First of all, we find that as I shift the temperature, we're going to find that the dominant wavelength of light shifts. So a cold object still is actually a black body source. It turns out that you're a black body source, but your radiation is in the infrared region. So this is essentially low energy, long wavelength. This is also how infrared goggles work, is you look at, you're able to detect things that are slightly higher in temperature than their surroundings through black body radiation. However, as you heat up an object, it actually moves, its peak wavelengths start to move into the visible spectrum. And then you start with long wavelengths like red light, move your way towards yellow, and eventually, if you get really hot, you move towards blue, violet, or even into the UV. However, it's very hard to move that high. And again, illustrating hotter the object, shorter the dominant wavelength. So the more blue shifted the object will be. And again, we model this as a hollow sphere with light rebounding inside that's slowly emitted. So what we're going to try and do is match up a theory that will predict this sort of behavior. And so we can take this behavior and fit it to two key empirical relationships. So in other words, we're going to take this idea and we're going to put some numbers to it. The first one was Stefan Boltzmann's law. So this is the idea that as I heat up my object, not only does my wavelength shift, but also the amount of light shifts. And it turns out that this is proportional to the temperature to the fourth power. So this is to the quartic power with a constant equilibrium with a constant of proportionality, which has no dependence on any other property. So again, if I know the temperature, I can figure out the total amount of energy released from a black body source. And you'll notice that it's quite stellar. And this is actually one of the key ideas of, say, a light bulb. We heat it up and we start seeing a drastic increase with the amount of energy released. The other empirical relationship that we're going to try and fit is called Wien's law. And this essentially relates to that more important observation we were talking about, which is what is the peak wavelength of the object we're interested in. So it turns out that we find is that there's going to be an inverse relationship in between wavelength and temperature. So the hotter the object gets, the lower the wavelength. The colder it gets, the longer the wavelength to essentially compensate. And this is going to be a direct inverse relationship. So directly proportional. You can imagine treating this as the wavelength equals a constant over T. And so what we need to try and do is find a way to predict these behaviors, because again, these are wonderfully useful laws, but they tell me very little about how this energy is bouncing around inside my object and how it's being released. So again, these are just straight experimental fitting. So classical physics wanted to go ahead and try and solve this problem. So the explanation actually makes a certain amount of sense at the time, especially in the era before atoms. So we start with the idea that this light comes from resonant vibrations within that black body. So I have a solid object. I've got essentially vibrations going through the object. So I've got electromagnetic waves inside my object. Occasionally they're released from the material, and then that's what I'm seeing. And so what we can try and do is predict the total energy inside a black body based on the amount of energy that's present in any given wavelength. And again, this will also show a temperature dependence, because we know that, first of all, the energy is temperature dependent, but so is the relationship of what wavelength dominates at any given temperature. So what we do is we say that we should be able to get the total energy released from the object based as an integral of the energy at any given wavelength times the differential of that wavelength. So a smooth integration over this function should hopefully feed back the total energy released by a black body. So a good place to try and start with this was a classic physical relationship that we actually used a fair bit in thermodynamics. And this is going to be the idea that each of these wavelengths should be an independent oscillation. So each of these wavelengths should represent an independent vibration inside of my object, and thus is considered a degree of freedom. Well, we found out last semester that classical physics predicts that every degree of freedom has an energy of 1/2 kT. So again, 1/2 the Boltzmann constant times the temperature of the system. So that should simply be the spectral density. So then if you integrate the system, you have to be careful, because you have to integrate it over 3 dimensions, which is how we end up producing an inverse quartic relationship, because this essentially will stand in for the volume of my system. And the kT is, again, corresponding to the spectral density. And again, 8 pi also is going from a linear relationship into a radial. So again, some tricks going from a linear behavior to a radial behavior, but otherwise should hopefully make sense. Now, the problem happens in when you try and fit this spectral density and compare it to experimental values. So this predicted Rayleigh-Jeans value gives actually pretty good behavior at long wavelengths. However, as soon as you go to low wavelengths, it breaks down and it breaks down hard. So, most notably, what you find is that it quickly goes exponential because as my wavelength gets smaller and smaller, my my spectral density starts to approach infinity. Turns out I can't have an infinite energy density, so this is a slight problem. And this is what's called the ultraviolet catastrophe. Because as soon as we hit the UV region, we're predicting an infinite density of energy. And we can actually kind of logic out how they would have expected to kind of get to this Rayleigh Jean sort of behavior. And the reason why is because under long wavelengths, I can only fit in a small number of individual vibrations inside of my black body. However, and each of those vibrations has, say, a half kT. And it turns out that's actually fairly true. But something weird happens when we go to low wavelengths. Because under a classical behavior, as I go to low wavelengths, I could fit almost an infinite number inside of my sphere. But the problem is that while you could technically fit an infinite number of vibrations, they certainly don't have a half kT energy. Experimentally, we expect to find some peak value, and then as I go to very small wavelengths, they contain no energy whatsoever. I have no emission in these low wavelength regions. So it became very clear that something was missing out of the classical model. We're going to try and fix that next time. However, I do want to actually end on an important idea. And that's that this Rayleigh genes, one of the important names you'll find here is Rayleigh. So this is Sir Walter Rayleigh. This is the person who originally came up with most of our descriptions of the behavior of light. This is one of the most important figures in original classical physics. And it's important to note that no matter how big the name, they can still get a problem wrong. And this is one of the powers of science. The power of science is it does give us a method of self-correction. You can see when things have gone wrong. So it doesn't matter if you happen to be the winner of the 4th Nobel Prize in physics. You still get things wrong sometimes, and it turns out that might be what you're remembered for. So next time, we're going to go ahead and move on to the idea of how we can use quantum mechanics to fix the ultraviolet catastrophe. Until then, take care.